Geometry kids, I've got a sick kiddo at home, so I am recording this lesson for you. I don't have my document camera, but I'm going to record this with my smart ink pen and stuff, so bear with me with technology. So 12.4 is geometric probability. On the back side of this sheet, I'm going to give you a couple formulas that you need to know for area. So like area of a circle, area of a rectangle, area of a triangle, that type of thing. I'll give those to you if you don't already know those, but they start us off with just like line segments and the probability of landing a dot on a certain portion of a line segment. So if I'm given this line AD, and like let's say I would take a point and I'm just gonna smack that point on that line somewhere, and I want to know the probability that it lands on BC in relationship to the whole line, I would just do the length of BC over top of the entire length of AD, so BC over AD. You can see that more in example 1. Point X is chosen at random, and I know that point X is going to live somewhere on the length of LM. I'm just putting him on there somewhere. And I want to know the chances of him living also on KL. So more specifically, if he lives in this segment here. That segment has a length of 7, and the entire length of the segment from J to M is 14, I think. So he has a 1 in 2 chance of getting smacked on that line and living in the region KL. Okay, now that didn't really make a whole lot of sense as a story problem. How does this work? Where does this apply to real life? So example 2 says is more real life scenario. A Chicago Transit Authority train arrives or departs on a station like Addison on the red line every 15 minutes. Assume that you arrive at Addison on the red line at a random time. What is the probability that you will have to wait 5 minutes or more for a train? Okay, so I'm going to put this as like a line segment here, and if we just kind of think about what's going on with this scenario. Worst case scenario is I show up to get on the train, and the train is leaving basically. If that happens, I'm going to have to wait 15 minutes for another train to come. So worst case scenario, I show up as it's leaving, and I'm going to have to wait this 15 minutes. Best case scenario is I show up and the train is coming as I show up, so I'm going to have to wait 0 minutes. Okay, so anywhere between 0 and 15 minutes is my wait time, basically, and I'm going to segment off this line segment here so we can kind of see what's going on. So assume that you arrive on to get on the train at a random time. What is the probability that you'll have to wait 5 minutes or more for the train? So 5 minutes or more is any segment or any amount of time that's between the 5 and 15 mark. And you can kind of see with this line segment, 5 to 15, that's 10 minutes out of a total of 15, or if you can just see the relationship that the line segment is, that's 2/3. So 2 out of 3 times I'm going to have to wait at least 5 minutes to get on the train. Okay, so realistically, I want to kind of plan that into my, my time, so that 66% of the time, basically, this is what 66% is. 66% of the time, I'm going to have to wait more than 5 minutes. So, and then we have the area probability ratio, and so I'm gonna kind of see both of these screens at the same time. This one kind of relates to like the target effect. This one is a skydiver landing on a target. So basically scenarios that have to do with this is kind of like saying, okay, if I shoot a dart at this target, or a skydiver is landing on that target, and I know that they're going to land somewhere on this target, what are the chances that they land in the red area? Okay, and that's exactly what this question is asking. Suppose a skydiver must land on a target of 3 concentric circles if the diameter of the center circle is 2 yards. Okay, stop. I'm going to go ahead and mark this as 2 yards. Pretend that line is straight. And the circles are spaced 1 yard apart. So from here to here is 1 yard, and from here to here is 1 yard. And I'm going to go ahead and mark that on the other side, because you'll see in a minute why That is important information. So, what is the probability that the skydiver will land in the center circle? So basically, I'm wanting to find the area of this center circle in relationship to the total area. So the area of circle B is kind of like what's going on here versus the area of the rectangle. The area of what I'm trying to find over the total area. Area of region B over area of region A. So the center circle is going to be my top one. So I'm going to put small circle over large circle, basically, is what I have going on here. Small over large. All right. So the area of a circle, I give this to you on the back side, but area is pi times radius squared. If you did not know that already, write that down. I'm going to give you all these on the back side. Pi r squared. And then the center circle, because they gave us the diameter is all the way across the circle, that's 2. The radius is actually going to be 1. So we have 1 squared times pi, basically, is the area of that top circle. Okay. Now, the large circle, all the way across here, here's 1 to 1, 1, 1, 2, 1, 1. So the diameter of that circle is 6, which means the radius is 3. So I have 3 squared times pi. So that gives me the area of the small circle over the area of the large circle. Now, don't get out your calculators. Don't start multiplying that stuff together because let me show you what happens here. 1 squared is 1. 3 squared is 9. And the pi, since I have a pi on the top and a pi on the bottom, those just cancel out. So basically what's happening here is if my skydiver lands randomly on this surface, maybe he lands here, or he lands here, or he lands here. Oh, you can't see that. Basically, he has a 1 in 9 chance of landing on that red circle. Okay? Next page. We've got, this is the last example. Example 3. Use a spinner to find each probability. The probability that the pointer lands on yellow. I think these are printed in black and white on your screen, so I apologize. Maybe label these as yellow and purple and blue and red and green, so you know which segment is which. Okay, so there's that for you. The probability that a pointer is landing on yellow. Now, consider this information that we have here. 105 degrees, 70 degrees, 50 degrees, okay? When they give it to us like that, degrees are based out of 360, okay? A lot of people look at those and they'll say, oh, that's out of 100. No, that would be percent. So like 90 degrees is actually 25% of the circle. So don't get those confused, okay? When we're dealing with degrees, 90 degrees is out of 360. So the probability that the pointer lands on yellow is 45, not out of 100, 45 actually out of 360. There's 360 degrees in a circle. So be very careful of that. 45 out of 360 reduces, it is 1/8. So I have a 1 in 8 chance that my pointer is going to land on yellow. Okay, pointer landing on purple. Purple is 105. And again, that's degrees, okay, not percent. So 105 over 360, and oh boy. If I divide by 5, that's 21 over 72. Is that right? 21 over 72. Yes, but that can reduce even further if I divide by 3. That's 7 over 24. There we go. That's better. 7 over 24. Those are my chances. Okay, so reduce those as far down as you can. And then find P, the pointer landing on neither red nor blue. Okay, red and blue are here. Rather than adding these 3 sections together, I'm going to find what's called the complement. I don't know if we talked about that in this class before. Complement. I can't write very fast. E-M-E-N-T, complement. Okay, and I'm going to do actually finding red and blue together. 70 and 150 is 120 over 360. 120 over 360 is 1/3. Okay, so I have a 1 in 3 chance of selecting red or blue, but I want neither red or blue. So if 1 in 3 chances are my chances of red or blue, then I have a 2 in 3 chances of not getting red and blue. And that's called finding the complement. You actually find what you don't want first, and then you go ahead and subtract that and find what you do want, okay? All right, here's some area formulas that you need to know and write down. So circle is pi radius squared. Rectangle or square is the same. It's base times height or length times width, whichever one you want to think about. Triangle is 1/2 of the base times the height, or you can do base times height divided by 2. So I went ahead and gave a little example here so you can kind of see what this looks like. Pi times radius squared. If my radius is 10, 10 squared is 100. And 100 times pi, I can actually do this in my head. Pi is 3.14159. I'll just say that's as far out as I can go. If I take 100 times that decimal, I just move the decimal place 2 places. So it's 314.16 approximately is going to be the area of that. And that would be in like inches squared, whatever my units are. We'll just say they're all in inches. So inches squared, there you go. Rectangle, base times height, 3 times 4 is 12, and that is it. Inches squared. And then last, for area of a triangle. The reason why it's 1/2 base times height, if you notice these kind of go together, base times height, but this is half of it. If I were to make this into a rectangle, this triangle is half of what the rectangle would be. So I do 6 times 10, and I can divide that by 2. 6 times 10 is 60, divided by 2 is 30, and that's 30 inches squared, or whatever my units are. Okay, so those are things that you might need to know for when you do the homework assignment. One more thing that I will tell you about this guy, if you are going to type this into your calculator, don't type in 3.14 because that answer will be rounded. You have a really, really, really nice pi button on your calculator. Locate it and use it. Otherwise, your answer will be kind of off by a little ways, okay? So that is all I have for you. Hopefully you have a good rest of your day, and this is the homework assignment that I have for you guys for geometric probability. So go ahead and write this down. I'll post this on Google Classroom as well, but page 884, 6 through 34, the evens. There you go.